So I'm going to change gears a little bit and talk about what we can learn about asteroidal boulders through measurements of their associated fireballs. So as Mark nicely introduced in the previous talk, of course, we have meter-sized and larger objects that hit the Earth, and in so doing, they undergo rapid mass loss and light production. So everything from decameter-sized objects like Chelyabinsk here to smaller meter-sized objects that in some cases are quite strong, such as the Carancas impactor shown over here. All right, so from spacecraft measurements, Bennu, Ryugu, Itokawa, we kind of have a picture that's emerging that many of the boulders, decimeter, meter-sized boulders on the surfaces, have fairly high porosity based on remote sensing inferences and modeling of what we see in those remote sensing data. Seems like macroporosity may dominate in some of the larger boulders. The typical macroporosity from Ryugu is in the tens of % range. Bennu is quite high as well. The tensile strength appears to be pretty weak. Again, a lot of this is based on modeling and some assumptions, but it comes in at sort of order of megapascal. And just for reference, typical meteorites in the lab have compressive strengths of 10 to tens to order 100 megapascals. So these boulders in situ appear to be much, much weaker than equivalent objects that we have in the lab for study. We also suggest, at least some of the studies on Ryugu in particular, have suggested that larger boulders can survive impacts, but again, their failure thresholds are in that few tenths to a megapascal range. So the sort of summary we have, the picture we have is that decimeter and larger sized objects that are on the surface of Bennu, Ryugu, and Itokawa are weakly cohesive, highly porous, seem to have failure strengths in the few tenths to maybe a megapascal range. But we don't really have a lot of direct measurements for smaller boulders, things that are under a meter in size. And of course, we don't have measurements for a range of parent bodies beyond these two C-types and S-type asteroid. So the question I want to try to address in this talk is, what can fireball measurements do to add to this picture? So putting it another way, what is it that I can actually get from fireball measurements that might allow me to add to this picture? I want to quantitatively assess the strength of the material that makes up these impactors. Okay, so let's start right at the basics. So here's a picture of a fireball. This is everybody's favorite fireball. This is Chelyabinsk. There's over 1,000 videos of this particular object, which hit in February 2013 over the Russian city of Chelyabinsk. I show this one because probably very few of you have seen this. This is actually the person who was closest to the terminal ground impact point of the fireball, which is why the fireball just appears as sort of a star-like object coming right towards them. They were actually just a little bit to the east of the impact point of the main meteorite in Lake Chervakol in Chelyabinsk. But what you'll notice here, and this is typical of fireball measurements, we have a few specific things. We see the brightness of the fireball over a period of a few seconds. That brightness is a direct indication of how much material is being ablated from the object. We also see, in some cases towards the end, particularly with Chelyabinsk, you can actually see some fragments that are streaming off of the body. So in some instances, we can directly measure the fragments, their sizes, and their physical characteristics. So effectively, what we're trying to do is we're using the atmosphere as a detector. The atmosphere is crushing and destroying these meter-sized objects, and we have a few seconds to extract whatever information we can to try to, through models, infer properties of the underlying body. Now, the advantage this has over in situ measurements is we're literally taking from the outside inward, breaking apart the meteoroid, throwing it into the atmosphere, and based on how it behaves, we can make inferences about its interior structure, about the fraction of material that's weakly held together, and so on. So one of the principal things we do in these sorts of measurements is we're assuming that the object fragments when its compressive strength is exceeded by the dynamic pressure of the atmosphere. So in other words, as this thing's moving through the atmosphere, it feels a dynamic pressure from the hypersonic airflow. It goes as roughly the mass density times the velocity squared. So based on the height at which you see fragmentation, you can uniquely assign essentially a strength to that fragmentation release. And then based on the subsequent evolution of the light production, you can make at least educated estimates, I would say, of the distribution of material fragments and mass. And in general, of course, this means that material released earlier in flight typically is associated with weaker material. And so for a given speed and mass, the deeper something penetrates, the stronger it is. It's a very simple concept in that sense. Okay, so Chelyabinsk is definitely the best observed large impactor. It was about a 20-meter sized object. We have a huge amount of data to go with Chelyabinsk, but for the purposes of trying to understand its structure, we have a couple of simple things we can infer. So if we look at the brightness of Chelyabinsk as a function of time, so this is time and equivalent height. This is how bright the object was, how bright the luminosity of the fireball was. We see a couple of little humps, one here at about 45 kilometers height, and another one here after the main fragmentation, after the peak brightness here at about 24, 25 kilometers height. So this early perturbation in the light curve is associated with small amounts of material, less than 1% of the mass, in the form of sort of gram to kilogram sized material that's been released. Then at about 42 kilometers, the whole object just comes apart under about a megapascal of pressure. And between 1 and 5 megapascals of pressure, the object just basically completely disintegrates. And that's probably a pretty good estimate of the overall global strength of the object that was holding, or of the tensile strength holding Chelyabinsk together. Now, after the main fragmentation, we see a number of fragments, about 10 or a dozen meter-sized. You could think of them as inclusions that survive past this 5 megapascal crushing dynamic pressure. Some of these get down to of order 15 megapascals pressure before they fragment. These individual fragments are basically highly competent inclusions that only make up about 1% of the mass, but are more than an order of magnitude stronger than the rest of the material. So from Chelyabinsk alone, we already have a picture of small amounts of surface material coming off, huge amounts of material of order a few megapascals crushing and then being released, and then a tiny fraction of the overall mass in the form of these sort of coherent boulders. So this is Chelyabinsk, a specific example, but how can we extrapolate more generally to the fireball population as a whole, right? We want to look at more than just Chelyabinsk. So this is a busy slide, but I'll describe this in a little bit of detail. Basically, when we look at fireballs, if we want to measure the relative strengths, which material breaks up easier than other materials, we have a couple of specific measured quantities that we can use. So the first and most commonly used, I'm showing it here in the upper left-hand corner, is called the PE criterion. Don't worry about the equations, but the PE criterion conceptually is just the idea that something that penetrates deeper in the atmosphere is stronger. That's it. The PE here stands for the mass density at the end height of the fireball. So you look at how deep the fireball penetrates, and the deeper it penetrates, the larger is this PE number and the stronger this object is. So if you look at the numbers, things over here, this is PE versus number. This is from a collection of Prairie Network fireballs taken in the 1960s. These are all strong material that we typically would associate with chondritic type objects. As you move to the right, it's weaker and weaker material. Things like carbonaceous chondrites are found here. And the tiny fraction of objects over here are extremely weak things that end high in the atmosphere we would associate with cometary material. Now, in addition to the PE criterion, we can also look at how things ablate, just the amount of material overall that is released as the object travels through the atmosphere. We do this through what's called an ablation coefficient. We measure this in a model. So the advantage here is the more something appears to give off material or ablate, the easier it is to break the material up, the weaker is the material. That's essentially the concept behind this. The downside of this, though, is you have to have a model to interpret this ablation coefficient. For some ground-based data, you have very, very high precision metric measurements of fireball flight. And in those cases, you may see individual fragments, and you may see how individual fragments are released and decelerate. And in that case, you can actually work out the dynamic pressure at which those fragments are released. And that's something that, again, was done on a similar set of prairie network photographic data from the 1960s. And in so doing, you get this sort of distribution of gross fragmentation pressures, that is, of the order of half to 1 megapascal. So we're seeing a picture here already that a lot of the meteorites, the fireballs, are fragmenting at very low dynamic pressures, much, much less than the compressive strength of meteorites in the lab. And in keeping with this notion of the dynamic pressure being very important, Borovichka just a few years ago introduced this concept of what's called a PF, or a pressure factor. And it's similar to a PE criterion, but basically, instead of looking at the end height, you look at what is the highest dynamic pressure a fireball survives. So if you just look at the flight and you measure its velocity, you can measure what's the highest pressure that it experiences, normalized to mass and velocity. So again, the idea here is things that can survive to higher dynamic pressures are more resistant to ablation. These things are quote unquote stronger. All right, so if I look at a series of survey measurements done from ground-based cameras, this was done by the European Fireball Network over the course of 1 year in 2017. If I look at the pressure factor here, so things up here are more resistant, they experience higher pressure, and I plot them as a function of velocity, and I color code by PE type. So the blue are the strongest material that survives deepest in the atmosphere. The yellow are things that tend to break up higher in the atmosphere. We see overall there is a correlation, that particularly at lower velocities, there's a lot of fairly dense, fairly strong, deeply penetrating material, and there's some, but not as many weaker material. So this is at centimeter sizes. You can extend this PF strength comparison to much larger sizes. I'm just showing here a few meteorites that have been measured, had their fireballs measured with sufficient precision to measure PF. And the essential point here is that ordinary chondrites have typically these fairly high PFs, meaning they're strong, and carbonaceous chondrites and some objects that we think there are no meteorite analogs that we have in our lab experience incredibly small PFs. In other words, they completely break up under very low pressure. Okay, so let's talk about some very specific things. So what we really need to examine exactly how fireballs come apart is to take metric and photometric measurements of high precision, kind of like what we had for Chelyabinsk, but obviously for smaller objects. And again, the group in the Czech Republic have done this with the European Fireball Network. And what they've done is they've looked at about 21 fireballs for which high precision photographic data is available. You get very precise measurements of velocity and height and brightness. And they've combined this to produce an estimate of how much material is released under what pressure. And to first order, you'd think, okay, these objects are coming in, they have cracks that are probably related by some sort of Abel distribution. So you should see sort of fragmentation as a continuum through pressure. And that's not what they see. It appears that at least for ordinary chondritic-like fireballs, there are sort of two stages to fragmentation. There's a lot of material that's released under a tenth or less of a megapascal, so at very high altitudes under very little pressure, and then a quiescent phase at a few tenths of a megapascal, and then again at a few megapascals, a lot more material is released. And they've interpreted this to mean that what we're seeing are these smaller objects have a lot of weakly cemented material. This is actually the majority of the mass that make these fireballs up. And then there's material that are weakened by collisional cracks or thermal fatigue that are represented in this sort of second stage of fragmentation. But this is a small sample.
You have 5 minutes left, Peter. Sorry.
Great. No, it's okay. Thank you. All right, so what we'd like to do is extend that ground-based measurements to much larger numbers and try to infer sort of the population of meter-sized objects impacting as a whole. To do that, we make use of a global system, US government sensor measurements. So these are fireball measurements derived from US government satellites that have measured about 1,000 meter-sized impactors hitting the Earth since the late 1980s. They produce data on the altitude, velocities, and total energy of these impactors, and most recently have produced detailed light curves. So the light production is a function of time for each impactor. And this has allowed us to go in and actually start making model measurements of where these things break up. And we find lots of end member kinds of bodies. So for instance, bodies that penetrate deeply come apart under sort of high pressures, 10 megapascals pressure. Here's another example of an object that meter-sized object, actually about 4 meters in size, completely broke up at very high altitude under almost no dynamic pressure. And then the grains and dust just rained down and ablate lower in the atmosphere. So this thing broke up under less than a kilopascal of pressure, and just shows sort of that extreme range that we find in the strengths of these meter-sized objects. So if we try to put this all together in one chart, I'm plotting here velocity against the height at which we have the peak brightness from this US government sensor data. And I plot this because this is the data primarily available for all of these, for all of this data. Now, obviously, for each one now, we can go in with these light curves and do more detailed model measurements. And we've done that for a subset of these fireballs, but not for all 300 or so. That's something that's ongoing. And what I'm showing is just the dynamic pressure ranges. So this is the dynamic pressure, 1 megapascal, 0.1 megapascal, given this height and this velocity. And what you see is that most objects penetrate down to of order a few megapascals. Some get down to even 10 megapascals. There's a few that seem to break up extremely high in the atmosphere at a few tenths or even less of a megapascal. And we also have meteorites here for comparison. That is US government sensor fireball measurements for which meteorites have been produced. And we can sort of map onto this chart sort of our estimates of where the different PE classes fall. And they're basically consistent with the fireballs that have produced meteorites. Okay, so to sort of cut to the chase, when we measure the dynamic pressures from these, all of these fireballs, 327, we measure the dynamic pressure at peak brightness, we get a distribution that looks like this, that these things typically get up to a few megapascals in pressure at their peak brightness. But that means that their earliest fragmentation is earlier. And the red bars here are a subset of about 30 fireballs for which we were able to make detailed models to match the light curves. And we find that they typically fragment at a few tenths to maybe up to a megapascal of pressure. And if we take those modeled events and we just look at, when did they first fragment and what fraction of material is lost, we find that the things that fragment earliest tend to lose most of the material earliest in flight. Things that fragment later tend to lose less material later in flight. Okay, so what kind of overall summary can we get? And most of this, I would say, is driven by the Borovichka et al. 2020 study, but it's informed by and consistent with the US government sensor data, at least to the points that we've been able to analyze it so far. What we see is we don't see a continuum in fragmentation strengths, particularly from ground-based measurements. We see a couple of distinct stages. Early fragmentation that typically for smaller fireballs anyway is where most of the mass is released at a few hundredths to maybe a tenth of a megapascal. Second stage of order, a few megapascal. And then for some larger fireballs, we see some competent material that have dynamic pressures that are able to survive up to tens of megapascals. And again, this suggests to us that these meter to decameter sized objects probably are composed of not monolithic bodies, but a lot of cemented regolith and soil that makes it the majority of the mass, smaller amount of collisionally weakened material, and then a few more competent fragments deeper down. Thank you very much.